Work, power, and machines. This is a this is something you should know, but it's a hard concept to understand. So, what is work? If y'all looking at the PowerPoint, you're cheating. Huh? Say there. So it's force. It's it's force times distance. So these are animations. This is not my video, by the way. Somebody else. The product of force applied to an object and the distance through which the force is applied. So we apply force with a pressure. We have a pressure, by the way, and then create a force, and then something's got to move. Everybody okay? So y'all mowing the lawn. Don't look at it. There's work being done. All right. Weightlifting is work being done. Moving furniture is work being done. Pushing against the locked door is work being done. No. No, because you don't have distance. Yeah. So yeah, y'all can stand over here all day long and push against that wall over there and you're not doing any work. Swinging a golf club. One lawnmower. Yes, 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 no. That's probably why I had it hidden, by the way. Calculated work. So why do we calculate work? Yeah, force times distance. So if a guy is running, if a guy covers the same distance in half the time, is they're doing more work? No, has nothing to do with time. Force is work. Force is force times distance, right? You understand what we're saying? So you produce more power. So power is the rate of doing work. So power is the rate. So when we deal with power, that's how fast you do things. But work is force times distance. So technically, if I ran the same distance at half the time you did, we still do the same work. All a part of the work must act in the direction of the motion. Do you do more work when you finish a job quickly? No, because it has nothing to do with time, right? Work does not involve time, only force and distance. No work is done when you stand in place holding an object. Uh, so work equals force times distance. We know that. So there's we don't use Newton meters over here. It depends if you get into a German plant here. We have quite a few now. They might be dealing with Newton meters. Most of the time we deal with pound per feet per pound, foot pounds. Most people call it foot pounds. Then we have the joule, one Newton meter. So this is another. And we don't need to know this because these are just not to know. Power. So we understand power. So how quickly work is done. So work, so power, so if I completed a job in half the time, then I don't do more work, but I produce more power. That makes sense? Amount of work done per unit of time. If two people mow two lawns of equal size and one does the job at half the time, who did the most work? Well, the one that completed it faster, right? So the same work, different power exerted. And we're not going to do it. Work does not involve time, only force and distance. No work is done when you stand it. I probably did. All it does is just hitting the wrong button. So power is equal to work over time. Yeah. So if time goes up, time goes up, power goes down. If time goes down, power goes up, right? For the same job. The watt. Y'all know about this, guys, right? James Watt. So you think about all these things we use, like Kirchhoff's law and volt and ohm. Those are all what? Named after people. So we don't deal with joules per second. We deal with force times speed. That's what we use to calculate watts, right? So used to measure power of light bulb. Of course, the formula we use over here to calculate power. So power is equal to volts, which would be force times speed, is what we're using, right? So we're not using work over time. So what they're saying is work over time would be equal to power. So we're using force times speed. And of course, the force that we're using is volts. And the speed we're using is amps, right? So this is the way we calculate power. Now, electric bill is measured in kilowatts per hour. So if you ever look at the electric bill, that's what it says. You use so many kilowatts per power. So 1 kilowatt equals to 1,000 watts. Y'all do that, right? Hopefully. Horsepower is around, we usually say 746 watts per horsepower because it's close enough. It's probably not even exactly 400. So over here, we rate our motors in horsepower. And we're one of the very few countries that do that because it gives you no idea what it's going to cost you to run it, right? You understand that? All other places they usually use what they call kilowatts. So theirs is not rated in horsepower; it's rated in kilowatts. And of course, this is the rule of thumb here. So for every force of every horsepower, take around 446 watts to create horsepower. So that's what you would do if you got a motor from over there and you wanted to figure out horsepower, then you just divide it by 746, right? I'm sorry, yeah, divide it by 746, right? Or you could go. So this is basically how it came up with. What they wanted to do was uh, they understood steam engines. They understood how much work a steam engine could do. So they wanted to come up with a method of comparing a steam engine to a horse because everybody understood horses. So basically they came up and hooked this thing up and they basically drug a weight or pulled it up on a wheel. They had a pulley. And then they see how many horses would take to move the same weight over a certain distance. And that's the way we come up with horsepower. So it's really, the term horsepower was developed a quantity of power a stone horse can move 400. From what I understood, they used multiple horses, a team of horses. So then they could divide it out, right? You understand that, and get an average. So one horse might be able to pull it this, another horse might be able to pull it that. But if they hook them up in a team, then they could average it out and they'd get a more. So 1 horsepower motor would move the same weight as an average horse could move 1 meter in 1 second. So that's the way they came up with it. If y'all ever wondered, I had to move that arrow, by the way. I did modify it a little bit. You know, they had it pointing, right? So I did. That's true. So I did modify his PowerPoint a little bit. Machines. So this is where we really get into work, the different types of machines. So what does a machine do? Yeah, it makes it easier for us, right? A machine can change the size, direction, or distance over which a force acts. So of course, input force. So the figure how much work gain we do. So anytime we do gain, it's always out over in. That's I don't care if it's a gain of an amplifier or a gain of anything. This is the way we do out over, and it has no units. It's just a multiplier. So gain has no units. We do use decibels every once in a while. dB is just a method that we can represent very large and very small numbers with very few digits. So we use engineer notation. Now, what do we use engineer notation for? Well, we can represent very large and very small numbers with fewer digits, right? You understand? Well, that's what dB is. dB is we take the gain, and then we take the log of that. We'll take the common log. Anybody know what the common log is? It's what 10 would be raised to get that number. So that's what it is. So it's common log. So 100, the log of 100 would be 2. Common log. Natural log is real weird. It's over 2.73 or something like that. But that's all it is what 10 would be raised to get the gain. So I take out over in, and I hit common log, and it's going to say 10 raised to some power. And that's what the log is. The log would be the power that it's raised to. And technically, we refer to that as a bell. And if we multiply it by 10, we call it a what? Decibel. So if you ever heard of dB, you'll hear a lot about that in stereos and stuff like that, or communications. When you say you can have a bandwidth is set as at a minus 3 dB. So, but gain has no unit. So it's output force divided by input force. This is the way we figure out the gain of a machine. Two forces does two types of work: input, work in, and work out. Input force times the distance to which the force acts. Input distance, work output would be the work done by the machine. Output force times the distance. So that would be what? Everybody understand this? So it's work out divided by work in. That's the way we calculate the gain on anything. Can you get more work out than you put in? Work out will always be less than work in because of the efficiency of what we're transferring the work through, right? You understand? So we never get out as much as we put in. Work output can never be greater than work input. That would be nice. So you could eat, they could feed you your first bottle when you were born and you'd never have to eat again because you produce enough energy to stay alive, right? We could put a car in motion, it would stay in motion forever because we get more work out than we put in, even though people claim that. If you ever see that guy on YouTube, don't believe it. Mechanical advantage expressed as the ratio with no units. So mechanical gain has no units. But if we have a real large gain and a real small or real small gain, you might see it done in dB or decibels. The number of times a machine multiplies the input force. Multiple advantage equals to force, output force divided by input force. But the actual, this is what we call ideal. The actual advantage would be times efficiency. I'm sure he shows that pretty soon. Two types of mechanical advantage. We have ideal, which is what we just calculated, and then we have involves no friction. It's calculated differently for different machines. Usually input distance divided by output distance. Output force divided by input force. Actual, this is going to be what? It's going to be calculated the same for all machines. So what's this? Is output ideal times what? Efficiency. So when we teach transformers, we say, you know, the division ratio, if it's a 12-to-1, we just use that to calculate the output voltage, but it's not. It's never actually that. The actual formula would be what? Turns ratio times what? Times the efficiency of the transformer. And there's no transformer that's 100% efficient. So that means we might be putting 101 watts on the input, and we might be getting like 99 watts at the output. Because of what? Because of the efficiency of the transformer. It's just easier to teach ideal than it is to add that efficiency in there. Some motors actually in their nameplate tell you the efficiency of the motor. That's different mechanical advantages equals to 1 output force. This would be ideal, right? We can change the direction of the applied force. Oh, so this is, what do we call that thing? So what did you do? If y'all were about the same weight, you would put the fulcrum in the middle, right? You understand? But if somebody was lighter than you, you would change most of those things. You can move them around, right? They only gave you like 4 or 5 different positions you could put them in. Mechanical advantage is always less than 1. And I don't know. So first thing we're going to look at the efficiency can never be less than 1. Can never be over 1, right? I told you, I think I saw a video where a guy had a motor turning a generator, and then he flipped the switch, and supposedly he unplugged the motor. I mean, he unplugged the motor and it kept running because he said he was running the motor off the generator. Is that possible? I had a guy that wanted to. He says, "I got a great idea. We have these battery-powered tractors, forklifts at work." He says, "I'm gonna take a generator and I'm gonna hook it up to the wheels, and that way, while they're rolling around, it'll charge the battery." What did I tell him? I told him the battery's gonna run down faster. Now they do have cars that use the centrifugal force of the cars, guys. Like when these new cars, like when you're going downhill, they'll let off the gas, and the rotors are generators. That will charge your battery, but they're doing what? They're using the car, the energy in the car to charge your batteries. So we never ever can get out. Yeah, I don't know if he ever believed me, but we had a guy that thought he could take the stroke of a motor, and wherever he pointed that motor at, when it made that upper stroke, it would go in that direction. So he thought he could just shoot it up in the air. So he actually got a patent on it, by the way. So paid for a patent. Nobody else had it, so you can get patent on things that don't work, right? I know that. Some work is needed to overcome friction. Sometimes we have to overcome gravity too, when we do that. So percentage of comparison of work output to work input. And this is the important concept I want you to understand. We're going to skip through here so we can get into the different types of mechanical advantages. But you never, ever, 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 ever can get more work, no matter what video you see on YouTube. You can never, ever, ever, ever get more work out than you put in. And I know I told you about the guy that taught transformers. I know I told you that. The lever. So how does the lever work? So what we got to do to get more force, then what do we have to do with a lever? So what makes up a lever, by the way? A bar is free to pivot or move around a fixed point that we call a fulcrum, right? Fulcrum is the pivot point of the lever. So we have 3 different classes. And by the way, this is on. Anybody took the MSSC test? Yeah, I guess what's on there. These classes, by the way. Like we said, we got a fulcrum, and then depending on what we do, depends on what type of mechanical advantage you have on the lever. So, if your force is in this direction, of course, if you push down this one thing these Class 1 levers do is your force will be always applied in the opposite direction, right? There are 3 classes of levers based on the position of the effort of the fulcrum. So first class lever, anybody know what the first class lever is? Nobody knows? Huh? So it all deals with the position of the fulcrum. Where do we position that thing at? Huh? So the point of force and the effort is the fulcrum is going to be between here. So if this is the effort, sorry guys, I don't know what's causing that, and then this is the force, and the fulcrum. This is what a class 1 lever is. So a seesaw is a class 1 lever. Fulcrum is located between the effort and the resistance. So I said that wrong. So this would be the effort, and this over here would be the resistance. So where we put that fulcrum at depends on what mechanical advantage we have. If we put it directly in the center, then the 2 lengths are the same. So we're outputting on the resistance, we're inputting on the effort. So basically the formula is the length between this length divided by that length. That's not right. It's going to be this. Now, let me look at that. That don't make sense. Makes work easier by multiplying effort force. I was looking at a guy teaching how to do logic with the Allen Bradley PLCs, and he was doing a math, and it was funny. So we'll see this. So y'all see this. So everybody's played around with that. Everybody used one of these. So this would be the length of the effort, and this would be the length of the resistance. And of course that's a crowbar. Second class levers. So what would a second class lever be? I've used these several times. So second class lever is one of these. So here's your resistance, and then this right here would be your effort. Here they move in the same direction. So where do we have these at? Can y'all think of any? This is a second class lever. So nobody's ever got something where you're pushing back here, right? Wheelbarrow. Resistance is found between the fulcrum and the effort. Makes it easier by multiplying the effort force, but not changing the direction. Examples. So a door is an example. All right. Anybody ever try to open the door right up against the hinges? It's not. It's hard, ain't it? Yeah. Uh, nutcrackers, wheelbarrows. So these are all second class levers. Now here's the fulcrum. Here's the resistance, and here's the effort. So the fulcrum's out here. So here's the fulcrum, here's the resistance, and here's the effort. Normally you don't. And the further you go back, the more effort you can create, right? Does that make sense? Shovel. I don't know. At the fulcrum looks like it would be at the tip. Third class lever's effort is located between the resistance and the fulcrum. Does not multiply effort, only distance. So third class levers, we don't get any. In fact, it's hard. What you get out of a third class lever is you get speed. So what's some examples of third class levers? If you're not looking at slides, huh? Huh? So a third class lever, we would have the fulcrum right here. Sorry. My effort would be right here. And then my load would be out here. Sledgehammer. So sledgehammer. So your fulcrum would be your elbow, right? Yeah. Huh? Golf clubs, yeah, would be a third class lever. You get speed, so you're like this, and the end of that club is what? It's flying. Baseball bats, these would be third class levers. Uh, so you use a third class lever if you don't want to increase force, but you want to create what? Increase speed. Examples: baseball bats, tennis clubs, shovel. So somebody asked about a shovel. Of course, golf clubs. Oh yeah, lifting weights. So your fulcrum's right here, right? And your weight's out here on the end. So here's the different levers. First class lever, fulcrum somewhere between the load and the effort. Second class levers, the fulcrum's on the end and the load's between you and the effort. And then a third class lever, you have the lever, the fulcrum, the effort, and then the load out here. Any another break? Okay, so let's take a break, guys. 2 minutes. Are a little different than gears. So what we do, and we're dealing with, I guess you'd say speed. So it looks a little backwards because normally we use out over in. But what we're going to do with levers is we're going to take the lengths between the fulcrum and the load, and we're going to divide that into the length between the fulcrum and the effort. So that means the shorter the load, the more force you develop. So we used to we'd do that on purpose. So you'd put the long end on the other side, and then we'd go down real fast and make the other one go real fast up on the other side. I slung somebody off a seesaw like that one time. I felt bad about it. So this is why we get so much effort out of a crowbar, because here's our fulcrum. Oops, let me change colors. So here's our fulcrum. So what we would do is we'd take this length and we would divide this into this, this length, I'm trying. So it's input length between that and the fulcrum, right? Divided by output length. So mechanical advantage, levers, ideal input, length of the input, divided by the length of the output. Input arm distance from the input force to the fulcrum, and output arm length between the distance of the force and the fulcrum. So the longer you have it, and this is why I like crowbars, you get so much. I got a crowbar, it's huge. I could probably pick up a car with it. So what is it? Output length between the fulcrum and the effort, and then divided by the input length between the fulcrum and the load. Are we okay? The wheels of an axle, this is a little different. A lever that rotates around a circle, a combination of two wheels of different sizes. A smaller wheel is termed the axle. The radius of the wheel divided by the radius of the axle. So you get a mechanical advantage with your wheels on your tires, right? The inclined plane. Everybody know what an inclined plane is? So what would you think? What would you think we would calculate the mechanical advantage on an inclined plane? The length of the plane, right, divided by the length of the height. So stairs are an inclined plane. The slanted surface used to raise an object. Ramps, stairs, and ladders. Length of the ramp divided by the height of the ramp. Are you okay there? And B lesson 1. The wedge. Inclined plane that moves. Knives, axes, razor blades. Mechanical advantage is increased by the sharpening of the blades. So that's nice to know. The screw. So what is a screw? It's an inclined plane, right? Wrapped around the cylinder. That's all it is. So if you got a screw the same length, which would give you the highest mechanical advantage? Narrow threads or coarse threads? Y'all know what I'm talking about? Threads? Huh? Yeah, so the one that's got the most threads, right, on the same length, would have the mechanical advantage, because the inclined plane length is going up, but the distance would be the same. You know, so if I had a screw, and we come over here, and this guy here had threads like this, that are the same length, and then over here I had one, and threads are like this. And of course, this would give us the biggest mechanical advantage, because it's length over what? Height. So it'd be so thread size. So that's one thing that we look at. So we have coarse thread, we have fine threads. The ones that we torque down the most and hose the most loads are going to be a finer thread than the ones that are coarse, right? Inclined plane wrapped around a cylinder. The closer the threads, the greater the mechanical advantage. Bolts, augers, drill bits. Pulleys. So this is important too. So this is on the MSSC test. So pulleys, these are what we wrap chains around. Well, technically a chain would be a sprocket. Belts, ropes wrapped around a wheel, right? Either can change the direction of the amount of force Also, we can flagpoles, blinds, right? Curtains. This is a true story too. Well, I got in trouble for this. I broke the chain on the American flag when I was in elementary school because they left it wrapped around and it had a concrete wall, and I unwrapped it and I was swinging on that thing and it broke and the flag came down. So my mom and dad had to buy a new flag. I got identified by the coat I was wearing. So we held all our coats up in the back of the class, and they brought the girl that was out there, and she went over there and she picked my coat out. Uh, I did get in trouble for that, but it was fun. So pulley types, fixed, can only change the direction of force. These have a mechanical advantage of one, multiple, movable. These can multiply the effort depending on the number of movable pulleys we have. Guess it's going to be greater than one. Number of supporting ropes. So here's some pulleys. So here we have a fixed pulley. So it would give us, applied and press and out would be the same. Here we got, this guy here is advantage of one. This guy right here, we have two ropes, so this would give us an advantage of two, right? Then we get over this thing. I try to figure this out. Advantage of four, and I don't know how you count that. But so the more, so you'll see some of these pulley systems. But what happens is that the more of these have, you get advantage, but it moves slower. Have you ever seen that? So I've seen a lot of these on cranes. We had a, a 3,000 ton crane. No, was it three? It was 300-ton crane out at U.S. Steel, and they had these things looped all over the place. It's the one that they picked up the big old ingots full of melted steel, you know. So I guess here we go. So one, two, three, four, right? So that would give us a mechanical advantage of four. So if I put 400 pounds over here, then we could do what over here, 1,600 pounds, right? So the more ropes you have, the more ropes you have. Of course, uh, huh? No, these pulleys are just mounted. Yeah, these are just mounted in one unit. So that's just a so that would be like a bar that just connects them together. Compound machine. So what's a compound machine? Of course, a compound machine is one that uses multiple techniques to generate torque, right? A combination of two or more simple machines cannot get more work out of a compound machine than is put in. He really expresses that. So that's it, guys. Y'all got any questions on that? So